There is a single point of light sitting in a James Webb Space Telescope image right now that shouldn't be visible at all. Not because it's too dim, because of what it actually is. It's an individual star, one single point of nuclear fusion, sitting so far away that its light left home before most of the galaxies we can see today had even finished forming. To reach us, that light had to travel for nearly 13 billion years, through a universe that was still, for most of that journey, a young, chaotic, half-built place. By every rule of normal astronomy, we should not be able to see a single star that far away. Individual stars, no matter how bright, simply fade into invisibility long before you get anywhere close to a distance like that. And yet, there it is, captured on camera, confirmed, studied, and named. And it isn't alone. In the years since, James Webb has kept finding galaxies out at these extreme distances that are far too bright, far too massive, and far too chemically developed for how young the universe was when their light left them. Astronomers have a word for what this is doing to their models of how the universe actually works. They call it a growing chasm between theory and observation. And by the end of this video, you'll understand exactly what James Webb found, why a star that shouldn't be visible turned out to be visible anyway, and why some of the most respected cosmologists in the world are now openly admitting that something in our picture of the early universe isn't adding up. Let's get into it. To understand how we ever spotted an individual star sitting nearly 13 billion light-years away, you have to understand the cosmic accident that made it possible in the first place. In March 2022, astronomers using the Hubble Space Telescope announced the discovery of the most distant individual star ever observed, a discovery that immediately broke every previous record by a staggering margin. Before this find, the previous record holder for most distant known star had been detected at a redshift of about 1.5, corresponding to roughly 9 billion light-years away, itself already an extraordinary achievement made possible by the same basic trick of gravity we'll get to in a moment. Earendel didn't just edge past that record, it shattered it, sitting at a distance more than 4 billion light-years further away than anything found before it. They named this new record holder Earendel, an Old English word meaning morning star, a fitting name for an object that had been shining since close to the very dawn of the universe itself. Under normal circumstances, spotting a single star at this kind of distance simply isn't possible, even for a telescope as powerful as Hubble. Individual stars are simply too faint. What you can see at extreme cosmological distances are entire galaxies, whole collections of billions of stars, their combined light blending together into a single smudge bright enough to register. A single star, no matter how massive or luminous, gets lost entirely in that kind of distance under ordinary conditions. The math on this is genuinely brutal. Even the most luminous individual stars in the universe would, at a distance of billions of light-years, produce a signal so faint it would be utterly indistinguishable from the general background noise and light-gathering limits of even our best instruments. Earendel became visible because of a phenomenon called gravitational lensing. A massive galaxy cluster called WHL 0130708 happens to sit directly between Earth and Earendel's home galaxy, and the sheer gravitational mass of that cluster physically bends and distorts the fabric of space itself, acting like an enormous, naturally occurring magnifying glass. Light from anything positioned directly behind that cluster gets stretched, warped, and dramatically amplified on its way to us. In Earendel's case, astronomers estimate the lensing effect magnified its light by a factor somewhere between 4,000 and 35,000 times, depending on which particular model of the cluster's mass distribution you use. Without that fortunate, precise cosmic alignment, happening to place a distant star exactly behind exactly the right foreground galaxy cluster, Earendel would simply never have been detected. We got lucky, in the truest sense of the word, catching a needle in a cosmic haystack because something else entirely coincidentally lined up to hand us a magnifying glass at exactly the right moment. Earendel's host galaxy, nicknamed the Sunrise Arc, appears to us as a long, crescent-shaped smear of light, stretched and distorted by that same lensing effect from WHL 3708. Earendel itself doesn't sit blended into that smear. It appears as a distinct, separate point of light lying directly along a specific ripple in the lensing pattern, a location where the magnification effect happens to peak most strongly, which is exactly why astronomers were able to pick it out individually, rather than seeing it lost inside the general glow of its home galaxy. Hubble made the initial discovery, but it was the James Webb Space Telescope, arriving on the scene shortly after beginning science operations in 2022, that gave astronomers their first real detailed look at what Earendel actually is. Using its near-infrared camera, known as NIRCam, Webb confirmed that Earendel is what astronomers classify as a massive B-type star, a category of extremely hot, extremely luminous stars, far more energetic than our own sun. According to the data Webb returned, Earendel burns at more than twice the surface temperature of our sun, and shines with roughly 1 million times the luminosity. It sits, evolutionarily, on what astronomers call the main sequence, meaning it's a hydrogen-burning star in the relatively stable, adult phase of its stellar life, rather than some exotic dying remnant. Webb's instruments picked up something else, too. A subtle hint buried in Earendell's colors that Hubble's instruments hadn't been sensitive enough to detect. Massive stars like Earendel very often don't exist in isolation. They tend to have companions, smaller partner stars, locked in orbit alongside them. Based purely on the specific wavelengths of light coming from Earendel, astronomers found tentative evidence suggesting the presence of a cooler, redder companion star. Its light stretched by the universe's ongoing expansion into wavelengths only Webb's infrared instruments were sensitive enough to pick up. Nobody has definitively confirmed that companion exists. But the hint was enough to make Earendel look less like a solitary anomaly and more like a genuinely typical example of how massive stars tend to form, just observed at a distance nobody thought was achievable. To calculate that distance precisely, Webb's other key instrument, its near-infrared spectrograph, or NIR spec, measured Earendel's redshift, the specific way its light has been stretched by the ongoing expansion of the universe, at a value of roughly z equals 6, 2. That translates to light that has been traveling toward us for approximately 12. 9 billion years, meaning Earendel was shining less than a billion years after the Big Bang itself, because the universe has continued expanding throughout that entire 9 billion year journey. Earendel's actual physical location today, its present distance from Earth accounting for that ongoing expansion, is now closer to 28 billion light years away. Here's where the story takes its first genuinely uncomfortable turn. And it's worth being honest about it rather than glossing over it, because it's exactly the kind of detail that makes this entire field of astronomy simultaneously fascinating and frustrating. As recently as 2025, a team of researchers led by astronomer Massimo Pasquale at the University of California, Berkeley, went back to re-examine Webb's detailed spectroscopic data on Earendel, specifically trying to answer a deceptively simple question. Does the light coming from Earendel actually look like the light from a single star? Or could it instead be coming from something more like a dense, compact cluster containing many stars, blended together so tightly that gravitational lensing alone couldn't separate them into individual points? The problem, fundamentally, comes back to the same gravitational lensing effect that made Earendel visible in the first place. Because the exact amount of magnification produced by the foreground galaxy cluster isn't known with complete precision, there's genuine uncertainty about exactly how physically large the source of that light actually is. Pascal's team compared Earendel's spectrum directly against another confirmed object in the same lensed galaxy, a source known as Object 1b, which astronomers widely accept really is a star cluster rather than a single star, using it as a kind of calibration benchmark. The comparison didn't produce a clean, definitive answer either way. It left the door open, a meaningful, still unresolved possibility that the record holder for the most distant single star ever observed might, when all the data is eventually sorted out, turn out to be a small, unusually compact grouping of multiple stars instead. That's not a minor technical footnote. It's a genuine reminder of how difficult, how fundamentally uncertain observations at these extreme distances still are, even with the most advanced space telescope ever built, pointed directly at the object in question. And it's a pattern that, as it turns out, extends well beyond a single star and into some of James Webb's biggest, most celebrated discoveries. While astronomers have been puzzling over the true nature of a single distant star, James Webb has, at the exact same time, been quietly assembling a much larger, much more troubling pattern involving something far bigger: entire galaxies. Finding candidate galaxies at these extreme distances is only the first step, and a genuinely tricky one. Initial detections come from Webb's NIRCam imaging, scanning for faint sources whose colors suggest an extremely high redshift, but color alone isn't proof. As Brent Robertson, an astronomer at the University of California, Santa Cruz, and a member of the JWST survey team has pointed out, the farthest galaxies are also the hardest to accurately verify. And some early, exciting candidates flagged by Webb in its first years of operation later turned out to be imposters, ordinary, much closer galaxies, whose light simply happened to mimic the color signature of something far more distant. Confirming a genuine record breaker requires a second, more rigorous step: detailed spectroscopy using Webb's NIR spec instrument, which breaks a candidate galaxy's light apart into its precise component wavelengths and directly measures its redshift, rather than merely estimating it from broad color filters. In May 2024, an international team working on the JWST Advanced Deep Extragalactic Survey, known as JADES, announced the discovery of a galaxy called JADES GS Z140, confirmed at a redshift of about 14. 32. That number corresponds to a galaxy observed as it existed just 290 million years after the Big Bang, when the entire universe was roughly 2% of its current age. University of Arizona astronomer Kevin Hainline, who helped confirm the discovery, described the process almost like time travel from his own desk, tracking a galaxy's light back further into the universe's history than anyone had ever managed before. It replaced a previous JD's record holder, a galaxy called JD's GS13-0, which the same research team had reported back in 2022 at a slightly less extreme distance of roughly 325 million years after the Big Bang, a reminder of just how quickly this particular frontier has been moving since Webb first switched on. Then, in May 2025, that record fell again. A team led by MIT astronomer Rohan Naidu confirmed an even more distant galaxy, designated MOEM ZES14, sitting at a redshift of 44, corresponding to a staggering 280 million years after the Big Bang. In the team's own published paper, later peer-reviewed and formally published in the Open Journal of Astrophysics in January 2026, they described it, quite directly, as a cosmic miracle. What makes both of these discoveries genuinely unsettling isn't simply their extreme distance, it's what they look like once you examine them closely. According to NASA's own description, ZES14 is brighter, more compact, and more chemically enriched than astronomers had any reasonable basis to expect for something that early in cosmic history. The galaxy shows elevated levels of nitrogen, a chemical signature that typically requires successive generations of massive stars, living out full life cycles and exploding, seeding their surroundings with heavier elements, a process that should, by every standard model of stellar evolution, take considerably longer than 280 million years to produce in any meaningful quantity. The galaxy also appears to have already cleared much of the primordial neutral hydrogen gas out of its immediate surroundings, another marker of surprisingly advanced development for an object this young. As Naidu himself put it in NASA's own announcement, "With Webb, we are able to see farther than humans ever have before, and it looks nothing like what we predicted, which is both challenging and exciting." This isn't an isolated case of one unusually precocious galaxy. It's become a consistent, repeating pattern, and astronomers now have a specific name for it: the impossible early galaxy problem, sometimes also described as the mature distant galaxy problem. Before James Webb ever launched, the standard theoretical models astronomers used to predict what the early universe should look like were fairly clear on this point. Detecting any bright galaxies at redshifts beyond 10, distances well past what the Hubble Space Telescope could reach, was expected to be extraordinarily difficult. Those models predicted that early galaxies should be small, faint, and genuinely rare, requiring tens of hours of painstaking spectroscopic observation just to confirm a single dim, marginal detection. That is not remotely what James Webb actually found once it started looking. Team leader Vasily Kokorev of the University of Texas has described a consistent trend across Webb's entire mission. The telescope keeps finding significantly more high-luminosity galaxies, densely clustered together at these extreme early distances, than pre-launch models ever anticipated, in some assessments by roughly 100 times more than predicted. Weijin Shen, a postdoctoral researcher at MIT and co-author on some of the most recent findings, summarized the situation in remarkably blunt terms for a working scientist. There is, in his own words, a growing chasm between theory and observation related to the early universe, which presents compelling questions to be explored going forward. That's a genuinely significant admission. It isn't a fringe claim from outside the mainstream of astrophysics. It's coming directly from the researchers running the flagship surveys, published in peer-reviewed journals, describing a real, measurable, and so far unresolved gap between what standard cosmological models predicted the early universe should look like, and what James Webb is actually finding when it points its mirrors at that same early universe. To be clear about where the science actually stands, none of this means the Big Bang itself is somehow wrong, and it's important to separate the genuine, mainstream scientific tension from more fringe interpretations that have tried to seize on these findings. Some organizations skeptical of mainstream cosmology, including certain young Earth creationist groups, have pointed directly to these JWST results as evidence that the entire framework of Big Bang cosmology is fundamentally broken. That's not the position of the working astrophysicists who actually made these discoveries. Every scientist involved in these findings, Naidu, Shen, Kokorev, Heinlein, and their colleagues, continues to work squarely within standard cosmological theory, treating this as a puzzle to be solved within that framework, not evidence the framework itself needs to be discarded. What mainstream researchers are actively debating are several genuinely competing explanations for why these early galaxies appear so much brighter, more massive, and more chemically developed than expected. One leading possibility is that star formation in the extremely dense gas-rich conditions of the early universe simply happened far more efficiently and far more rapidly than current models account for, essentially compressing what should have been a slower, multi-generational process of chemical enrichment into a dramatically shorter time frame. Some researchers have proposed that the earliest clouds of primordial gas, without the complicating presence of dust and heavy elements that regulate star formation in the modern universe, may have collapsed into stars with unusual speed and efficiency, essentially skipping several of the braking mechanisms that slow the process down today. Another possibility centers on the types of stars being formed in that environment. Some researchers suspect the earliest generations of stars may have been disproportionately massive and short-lived compared to the mix of stars we see forming in the universe today, burning through their fuel and exploding far more quickly, and seeding their surroundings with heavy elements at a correspondingly accelerated pace. This idea, sometimes described as a top-heavy initial mass function, would mean the earliest starbursts in cosmic history produced proportionally far more giant, short-lived stars and far fewer small, long-lived ones than the mix we observe forming in galaxies today. A third possibility under active investigation is that a meaningful portion of the light coming from these ultra-distant sources isn't purely starlight at all, but is instead being boosted by rapidly growing supermassive black holes at the centers of these young galaxies, actively feeding on surrounding gas and radiating enormous amounts of additional light in the process, artificially inflating how bright and massive these galaxies initially appear compared to their actual stellar content. Webb has separately already confirmed the existence of surprisingly massive black holes at extremely high redshifts, black holes that, by standard growth models, shouldn't have had enough time to reach the sizes observed, adding yet another layer to the same broader puzzle about how quickly massive structures were able to assemble in the universe's earliest chapters. None of these explanations has been conclusively confirmed yet. That's precisely the compelling questions to be explored going forward that Shen referenced. But every one of them represents genuine, active, mainstream astrophysical research, working to refine and adjust our understanding of exactly how quickly stars, galaxies, and black holes were able to assemble themselves in the universe's first few hundred million years, rather than any suggestion that the underlying cosmological framework itself is fundamentally broken. Here's the part of this story that should genuinely give you chills, because we are almost certainly nowhere near finished. Every single record James Webb has broken so far, Earendell's distance in 2022, JWST Zephyr's distance in 2024, MOMZ-14's distance in 2025, has been broken by researchers actively expecting, and would in some cases openly predicting, that their own new record would eventually be surpassed again. As Naidu and his colleagues wrote directly in their own published paper on MOMZ-14, JWST itself appears poised to drive a series of great expansions of the cosmic frontier. Previously unimaginable redshifts, approaching the era of the very first stars, no longer seem far away. That's an extraordinary sentence for a scientist to write with a straight face, and yet it reflects exactly where this field currently stands. Astronomers are now seriously discussing the genuine possibility of eventually observing what's known as population 3 stars, the theorized very first generation of stars ever to form in the universe, composed of nothing but the raw hydrogen and helium left over from the Big Bang itself, before any heavier elements existed anywhere in the cosmos to be incorporated into a forming star. These would be genuinely alien objects by modern standards, likely far more massive on average than the stars forming in the universe today, burning hotter and living dramatically shorter lives before exploding, and for the first time in cosmic history, actually seeding their surroundings with the heavier elements that every subsequent generation of stars, planets, and eventually life itself would come to depend on. No one has confirmed a genuine detection of a population 3 star yet, but the same combination of tools that revealed Earendel and MOMZ-14, James Webb's extraordinary infrared sensitivity, paired with the natural magnifying power of gravitational lensing, is widely considered the best realistic chance humanity currently has of eventually finding one. Meanwhile, additional instruments are already being planned specifically to help resolve the mounting tension between theory and observation. NASA's Nancy Grace Roman Space Telescope, expected to launch as early as late 2026, provided its funding survives ongoing federal budget negotiations, is designed to survey much larger swaths of sky than Webb's narrower, deeper field of view, giving astronomers a broader statistical sample of these strange, unexpectedly bright early galaxies to work with, rather than the small handful of individually confirmed record holders currently available. Where Webb has excelled at finding individual, extraordinary needles in the cosmic haystack, one record-breaking galaxy or star at a time, Roman is specifically built to survey enormous areas of sky simultaneously, potentially uncovering hundreds or even thousands of similarly luminous early galaxies in a single coordinated survey, transforming what is currently a handful of individually celebrated discoveries into genuine large-scale statistical data. That shift from isolated record breakers to a broad representative population of early galaxies is exactly what astrophysicists say they need in order to finally settle which of the competing explanations, faster star formation, top-heavy stellar populations, or black hole contamination, actually accounts for what Webb keeps finding. Step back, and here's the shape of the whole story. We found a single point of light, magnified by pure gravitational coincidence, that turned out to be a massive star shining less than 1 billion years after the universe itself began, and we still aren't entirely sure whether it's genuinely one star or a tightly packed handful of them. At the exact same time, using the exact same telescope, we've been finding entire galaxies, hundreds of millions of them potentially waiting to be catalogued, that appear too bright, too massive, and too chemically mature for the amount of time the universe had actually given them to develop. Neither of these findings breaks physics. Neither proves the standard model of cosmology wrong. What they do, both of them, in slightly different ways, is expose the genuine, honest limits of how confidently we can currently claim to understand the universe's earliest chapters. Every time James Webb points its mirrors a little further back in time, it keeps finding a universe that got its act together faster, brighter, and more efficiently than the best models built before its launch ever predicted it could. Rohan Naidu said it about as plainly as a working scientist ever does. It looks nothing like what we predicted, and that's both challenging and exciting. That tension between a universe behaving exactly the way rigorous decades-old theory said it should, and a universe that keeps stubbornly refusing to, is precisely where the genuinely troubling questions in this story live, not in some hidden cover-up, not in a broken foundational theory, but in the simple, honest, and thrilling admission that we built our best models of the early universe before we ever actually had the tools to look at it closely. And now that we finally do, it's turning out to be stranger, faster, and more mature than anyone had any real right to expect. If this made you look at the night sky a little differently, let me know in the comments what you find more unsettling. The idea that our record holder for the most distant star might not even be a single star at all, or the growing pile of galaxies that simply shouldn't be as bright and mature as they are this early in cosmic history. And if you want to keep following James Webb as it keeps pushing further and further back toward the very beginning of everything, subscribe. Because by every indication from the scientists actually running these surveys, the next record is very likely already sitting in the data, just waiting to be confirmed.